Over the last 10 weeks, BlockScience has been collaborating with Olympus DAO to be creating a cadCAD model for the simulation efforts. In this kind of video series, we're going to be going through how the cadCAD model works and also some of the research that's been done to date. So let's dive in. In general, the executive summary here is that we've created this cadCAD model and we are going to be trying to contribute and building out in the future. The repository tree gives us an idea of all the different files that are in the system. But before that, we should probably actually skip to what cadCAD is. Now, cadCAD is the simulation framework that BlockScience has been developing over the last couple of years, and we are using this simulation framework here because it adds a lot of convenience and more high-powered utility towards simulation. If you want to learn more about it, cadCAD.org has lots of resources on how to get started, and it will be very helpful for having the baseline knowledge before playing with this model. Now back to the repository tree. We have a couple different things. We have two notebooks here, and they're going to be examples of how to do a single run and a parameter sweep run. We have a legacy folder that holds just some old notebooks that are no longer used but are still useful possibly in future endeavors. And then we have model. This folder right here hosts the actual engine of our simulation model. There's a couple different folders in here that hold different aspects of the kind of model. So for example, we have behavioral, and this folder has all the behavioral functions that are used within the system. You also have classes, which likewise has classes that are used within the system. Mechanism has the functions that do any sort of state update. We have policy, and this policy folder will be used for the different kind of policies. So if you think like RBS, the different policies that affect when different interventions take place, that's where it's going to be hosted, these policies, this policy folder. psub.py is the actual Python file, and that has the partial state update blocks. These partial state update blocks pull from psub functions, which is a folder that has all the different update blocks that are going to be used within the cadCAD model. Run.py is a Python file for the code involved in running the model. And then we have signals, and this signals is a folder that has all sorts of functions for creating random signals for use in the model. So for example, when we have bonds, we have bond disbursement patterns that maybe we want to be representing. We also have types, and types is a folder holding the types utilized in the system. And finally, utility, and that has all our utility functions for ease of use stuff. There's also, of course, requirements.txt, and also research, which is a folder with any sorts of research that's been completed. Right now, it just has one set of research, which is the research that BlockScience has kind of contributed on for this first version of the cadCAD repository. Now, a lot of the changes that have come with this Olympus cadCAD model are more around building out the infrastructure for cadCAD runs, but there's also been the addition of ohm bonds, which have been added in, and some of the research is around kind of volatility that comes with kind of the ohm bond. Then in general, we also have down here some of the model details. So within the repository README, you can see what parameters are being used within the system. For example, the demand factor, supply factor. And so we won't go through each one, but for anyone trying to understand the model better, this README will have all that information. Now, we can jump into the two examples of how to run, and this will allow you to make your own kinds of versions and test out different hypotheses. For the single example, we have parameters, and that's going to be all the parameters of the system. In this case, you can see that they are all arrays. You have to have them all be arrays for cadCAD models. In this case, when we're only doing a single run, we just want arrays of length 1 for each parameter. And we have this default parameters within the utility folder, and that will host kind of some of the default parameters for research or for baseline simulations. So the default params 1, we're pulling that in, and this is what we're getting out. We can also have changes to it by just, like a dictionary, indexing into the factors and changing them. So here we show how to change demand and supply factor to 0.01 and negative 0.01. There's also initial state, and that's coming out of the utility folder as well, and that gives us the different initial states that we can begin our simulations with. You'll notice here that it says none. That is actually because there's a further function, fill in initial state, that will fill in any of these values. Some of these values, they actually need to have the parameters first to understand what these values should be at the beginning. So essentially you will bring in an initial state and have your parameter set. You'll make any changes, and then this fill in initial state function right here will take that and fill in any of those values that are none in the beginning. For running the experiment, there's two different parameters you can play with. There's number of runs, which says how many Monte Carlo runs to do per parameter sweep. Right now, this is just a single example, so it's just going to be 2 runs overall. But when we have a parameter sweep, it's the number of runs times the number of parameter sweeps. There's also the number of steps, and so here that means the number of days within our simulation. And so we set these 2 variables, and then this load config function will load the experiment. Then we can actually run the experiment, and then finally do post-processing on the experiment. There's also some visualization libraries. So for example, plot all sims is one of the visualization options, and it'll allow you to plot out what all the variables are that you feed in. So if we say reserves in, reserves out. So that's for the single sweep. A parameter sweep is a little bit different. There's 2 ways to do it, and we'll go through both of them. Before we do that, one thing to know is that for parameter sweeps, this means that all variables that we assign here have to have either length of 1 or n. And by n, we mean it can be any value, but they all have to have that same value of n. So it's some variables can have length 1, some could have length 5, but none could have any other length besides 1 or 5. This is because for any of the sweeping variables, they need to be aligned. Anything that has a length of 1 will be taken as a constant throughout all the simulations. So for example, if demand factor here is 0.07, that means that for all simulations, it will be 0.07. However, if we go down here and we change it and say demand and supply factor, and we have 0.01 and 0.05, negative 0.01 and negative 0.05, we are now going to have simulations where we have 0.01 and negative 0.01 as one set, and then 0.05 and negative 0.05 as another set. We can then also just get rid of the bond creation schedule because we don't want to be playing around with any bonds in this example. Pull in the initial state, fill it in, and then finally we can run experiments based on this. When we have number of runs 3, but we have a parameter sweep number of 2, we're going to end up running 6 total runs with time step of 100. And then we have a visualization library for plotting all sims that we've seen before. We also have this plot grouped variable averages, and that is going to let us do things like group by demand factor and supply factor and plots the average of those groups. So you can see here lowered volatility when demand and supply is lower. We also have a Cartesian product sweep, and what this is going to do is say take as many variables as you want, and these can have any length, they could be mismatched. But what will happen is we'll find every single combination of all of these factors. So say 0.01 and negative 0.01, 0.01 and negative 0.05, 0.05 and negative 0.01, 0.05 and negative 0.05, and it will find all the different combinations. So you see here, demand and supply factor then are assigned out here, and we have 4 total. This can also be used in terms of like having create parameter sweep and apply, which is a function that then just applies it to our parameter set. So you can see that then we have here and here it's applied to. With run and visualize, what we're saying is we're going to take 3 runs, and then we have a parameter sweep of size 4, as we see up there. So 12 total runs, and we're going to run it again. And then we can actually group, and we see that now we have 4 different sets for the parameter sweep, and we can see the impact of some of these different kinds of parameterizations of demand and supply on natural price. There's one other note, which is just to know that within our model, the P subs, there is a couple different versionings of it. So we have our very basic P sub blocks, that's just the baseline, but there's also a version where we get rid of the RBS, and that was used in one research scenario. And we also have a P sub blocks for the Soros attack, which adds in some blocks related to kind of a whale. And for the ability to actually access this, what one needs to do is go in, and similar to how the research was done here, one would need to just actually pass in this p sub scenario options equals with whatever specific extra p subs or whatever other parameterization should be used. So that's the baseline how to be using the cadCAD model. And in the next kind of section, we can go through some of the research that has been done to date.